Our final topic is on the area of synthetic polymers. Now, a polymer is defined as a large molecule composed of many smaller repeating units. Now, these units can be the same. Those are called addition polymers. They can be different. If they're alternating, that's what's called a copolymer. And then you also have polyamides, polypeptides, which we saw in the case of proteins. The first synthetic polymers included polyvinyl chloride in 1838, polystyrene in 1839, and there have been many others. Today, there are about 250 billion pounds produced annually worldwide. Okay, so some of the classifications of polymers include, here's addition polymers or chain growth polymers. So this is polyvinyl chloride. This is the monomer, vinyl chloride. And these are the repeating units. Okay, you also have what are called condensation or step growth polymers. This chapter is on synthetic polymers, but we can think of proteins as being like condensation polymers. We split out a molecule of water to form amide groups. Okay, so here we have dimethyl terephthalate, and we do a transesterification with ethylene glycol. And this is the repeating unit. This is a polyester known as dacron. This is also the polymer mylar. This is used in clothing. Mylar is also used in balloons, for example. Right, so these are some important addition polymers. Okay, if the monomer unit is ethylene, that's polyethylene. This is used for bottles, bags, and films, like sandwich wrap. Plastic milk bottles are made of polyethylene. Okay, polypropylene, okay, where one of the hydrogens is replaced by a methyl group. Polypropylene, for example, is used in making prescription medicine bottles and yogurt, cottage cheese containers. Here's polystyrene. Polystyrene, in contrast to polyethylene and polypropylene, which are flexible, polystyrene is brittle. You have alternating carbons with benzene rings, and so the chains are more rigid. Polyisobutylene is used in specialized rubber. Polyvinyl chloride is used in vinyl plastics, films, and water pipes. Polyacrylonitrile is used in carpet clothing. Polymethyl methacrylate forms a very hard, strong, transparent polymer. This is lucite or plexiglass. Also used in paints. And polymethyl alpha cyanoacrylate. This is acrylic acid. Propanoic acid is called acrylic acid. And then we have a cyano group on the ethyl. And then polytetrafluoroethylene is Teflon. Teflon is a slippery material. The chains slide past each other. It's also chemically inert. Right, addition polymers have three kinds of intermediates. Okay, these include free radicals, carbohydrates, carbocation, sorry, and carbanions. Okay, so some examples of addition polymers include polypropylene plastics, polystyrene foam insulation, polyacrylonitrile, and polymethyl alpha methacrylate. Okay, so in free radical polymerization, we start off with benzoyl peroxide. This is, like most peroxides, it's unstable. All you have to do is heat it, and it forms phenyl radicals. And these phenyl radicals begin a chain reaction. They react with styrene to form this benzylic radical, okay, which is resonance stabilized. The radical then attacks another alkene, propagates another radical, and then it just keeps going until the chain can get anywhere from 100 to 10,000 units long. Okay, to stop the polymerization process, they may add a radical inhibitor, or in some cases, the chains will just join up with each other. Certain catalysts are used to branch polymers in order to give them special properties. For example, the difference between milk cartons and sandwich wrap. Milk cartons consist of polyethylene chains which are straight, and they coil together like rope, very strong and flexible. Branched polyethylene, called low density polyethylene, is what's used in sandwich wrap. It's soft and flexible. Okay, a second means of polymerization is cationic polymerization. And here we start with a Lewis acid, BF3, or sometimes sulfuric acid. Okay, we protonate an alkene, which generates a carbocation. Another alkene attacks that carbocation, and then the process keeps going. Boron trifluoride is a particularly effective catalyst. It just requires a trace of water or methanol as a co-catalyst. In order for this to occur, the intermediate must be a stable carbocation. Okay, so here you can see it's a tertiary carbocation. So these are some good monomers for cationic polymerization. Styrene. Okay, we also saw we could use free radical polymerization for styrene, but this produces a benzylic carbocation. Isobutylene is a good monomer because it produces a tertiary carbocation as an intermediate. Okay, anionic polymerization is a third type of addition polymerization. Okay, in the initiation step, okay, we can use a strong base like butyllithium, which will add to the acrylonitrile. And this works well because the cyano group is not only electron withdrawing, but it also stabilizes this negative charge through resonance. Okay, this anion then attacks another acrylonitrile, and then the process keeps going. Okay, here is methyl acrylate. Okay, and this is a good monomer for anionic polymerization. Again, just like the cyanoacrylate, the negative charge can be stabilized by resonance. Okay, I might mention one other anionic polymer, and that is going back here, polymethyl alpha cyanoacrylate. Okay, that is the monomer in superglue. Okay, in this case, we have a negative charge on the carbon as our intermediate, and this negative charge is stabilized by resonance both with the cyano and with the ester group. Okay, so all it takes is a little bit of moisture to initiate polymerization or hardening of this superglue. Okay, stereochemistry can often be important in the properties of a polymer. Okay, here we have what is called an isotactic polymer, in which the side groups are on the same side of the backbone. And then here we have a syndiotactic polymer. The side groups are on alternating sides. Okay, back, front, and so on. And then an atactic polymer is one in which the side groups are on random front, back sides of the backbone. Isotactic and syndiotactic polymers are stronger and stiffer due to their regular packing arrangement. Anionic intermediates usually give isotactic or syndiotactic polymers. Free radical polymerization is nearly random, and so that gives the branched atactic polymers. Okay, the Ziegler-Natta catalyst. This was developed by two Italian chemists, and this allows polymerization to be completely stereospecific, either isotactic or syndiotactic, depending on the catalyst. The polymer is linear and not branched. And examples of the catalyst include titanium tetrachloride mixed with a solution of triethyl aluminum and heated for an hour. Natural rubber is a soft and sticky material which is obtained from the rubber tree. The long chains can be stretched, but then return to their original structure. Side chains will slide past each other and be pulled apart easily. Okay, so natural rubber, or also called latex, is a polymer of isoprene, and it has all cis configurations, all cis double bonds. Okay, there is another polymer. It's called gutta-percha, and this is also a polymer of isoprene, but gutta-percha has all trans double bonds. And gutta-percha is found, like natural rubber, it comes from a tropical plant. And gutta-percha is used in golf balls, and it also makes up the membranes of doctors' stethoscopes. It has very good sound conduction properties. Okay, so here is a rubber tree on a Malaysian rubber plantation. Vulcanization is a process that was discovered accidentally by Charles Goodyear. He dropped some rubber and sulfur on a hot stove. And what the sulfur does is it provides cross-linking that strengthens the rubber. And hardness can be controlled by varying the amount of sulfur. Okay, so here this shows the cross-linking of the cis polyisoprene units. Synthetic rubber. Okay, the difference here is that we don't have the methyl groups. This, instead of isoprene, we're using butadiene as a starting material. With the Ziegler-Natta catalyst, a polymer of 1,3-butadiene can be produced, in which all the additions are 1,4 and the remaining double bonds are all cis. And this can also be vulcanized. Okay, copolymers consist of two different monomer units. Saran wrap is a copolymer of vinyl chloride and vanillidine chloride. ABS plastic, that's used in water pipes as an alternative to polyvinyl chloride. This is a copolymer of acrylonitrile, butadiene, and styrene. Condensation polymers are those that are formed by ester or amide linkages between difunctional molecules. Monomers do not have to add one step at a time. Small chains may condense into larger chains. The common types include polyamides, polyesters, and polycarbonates, and polyurethanes. Okay, so here is nylon 6,6. It gets its name from a 6-carbon dicarboxylic acid and a 6-carbon diamine. There's some other varieties of nylon, such as nylon 610. Nylon was originally developed as a alternative to silk. Silk became very difficult to obtain just before World War II because the Japanese were taking over much of the Pacific Islands. Okay, so here is a photomicrograph of a nylon stocking, a scanning electron micrograph. And shear stockings require long, continuous fibers of small diameter and enormous strength. Okay, here's nylon 6, which is made from a lactam, which is then polymerized. Polyesters, this is one that we mentioned a few minutes ago. This is Dacron polyester or polyethylene terephthalate. If you're interested in recycling, this is type 1 plastic. This is used for a variety of purposes. Dacron, Mylar, and it's also used to make soft drink bottles. Okay, polycarbonates are polymers that result from, for example, phosgene and bisphenol A. Polycarbonate is a very tough material. It's used, for example, in to make shatterproof eyeglass lenses. And bulletproof windows. Urethanes. Okay, these are polycarbamates. A carbamate has an ester on one side and an amide on the other. They're commonly made by treating an isocyanate with an alcohol or a phenol. And the reaction, because it's highly exothermic, it gives a quantitative yield of carbamate ester. Okay, so here's an example of a polyurethane. Okay, next we'll look at polymer crystallinity. Okay, here we see a partially ordered structure. And a linear polymer will have a high degree of crystallinity, and it'll be stronger, more dense, and more rigid. Glasses exist at low temperature in polymers, and they fracture on impact. At the glass transition temperature, or T sub G, crystalline polymers become flexible. At the crystalline melting temperature, or TM, crystalline polymers become a viscous liquid and can be extruded into fibers. Okay, so this is crystalline versus amorphous. Both will have a glass transition temperature. Whoops. The amorphous polymer above its glass transition temperature becomes rubbery, gummy, and then liquid. A crystalline polymer will have a sharp melting temperature. Plasticizers are compounds that are added to polymers to make them more flexible. A plasticizer lowers the attraction between chains and makes the polymer more flexible. It can evaporate slowly, so vinyl becomes hard and inflexible over time. Okay, and you may also notice that plastic containers and plastic toys over time can become very brittle and fragile when they were once flexible.